Hi, I'm Ben-Yaakov. This presentation is entitled Obtaining the Small Signal Response of a Resonant LLC Converter by PSIM Simulation. Power converters normally operate in closed loop. I am showing here a one feedback loop system in which we have a converter and output, could be voltage or current, a summing junction in which we compare the reference to the output or part of the output, generating the error signal. This goes into the compensator or controller, which then feeds a modulator. This output of the modulator could be PWM if this is a PWM system, or it would be a frequency, a changing frequency, varying frequency if this would be a resonant converter. The converter we're going to discuss in this presentation is an LLC converter, and I'm showing a half-bridge configuration. We have the two transistors, the two inductors, a resonant capacitor. I'm showing here a transformer, full bridge rectifier, filter capacitor, and this represents the load. Now the static transfer function of this stage, that is, as we move the frequency, this will be the output, and this is for different loads, starting from 0.5 ohm, this is this load, to 10 ohms, is typically shown like this. What we see here is really the resonant nature of this circuit. It has actually two resonants. At this point, for example, which is the resonant frequency of L sub R and C sub R, which is in this case 100 kilohertz, we see that the transfer function would be 1 because L sub R and C sub R are sort of canceling each other, and the transfer function between this point and the output is in fact 1. So this is the static transfer function of this converter. However, we are not interested in the static transfer function here. In this presentation, I'm considering the question of dynamic or small signal transfer function. That is, here is the system, which includes the converter, and I've added a modulator, and I have a bias point which is setting the carrier frequency, that is the switching frequency, around which I'm going to change the frequency by injecting a AC voltage added to the bias point. So in an AC analysis, small signal analysis, I'm sweeping this source over frequency. This is a small signal over the constant value, could be changing, but I'm interested, of course, in the ratio between V out, which will be also small signal or relatively small signal, depending on the gain, divided by V in. This is perturbation divided by the input perturbation, and this will be the magnitude, and this will be the phase. So this is what is required for designing the compensator. For the compensator design, I do need to have the transfer function of the system itself, of the plant. And this is what I'm going to discuss in this presentation, how to get this transfer function by simulation. Now, I should stress that this transfer function, although it sort of sounds the same as AC analysis of SPICE, this cannot be obtained by SPICE or PSPICE, because in an AC analysis of SPICE, what is really occurring is that the simulator will first linearize the system around the operating point, that is around the bias point. It'll linearize it. We have a non-linear section here, it's a bridge rectifier. We have also the driver. So it'll pick up a bias point and then linearize the system around it and then do a phasor analysis. And of course the output will be garbage. So this cannot be done by AC simulation of SPICE-derived simulator. One way to look at it is to ask, first of all, well, can we get some information from this static curve? And indeed, if you look at the slope here, this is the change in voltage as a function of frequency. This is frequency here, so we're changing the frequency, and there is a change in voltage. This is correct, except that it'll be only correct for very low frequencies. At high frequencies, the inductances and the capacitor and the other elements will affect the small signal transfer function. So you cannot get this information from the information that we want from this curve. So what we want to do is to get the small signal from the excitation to the output, and one way to do it is to do a time domain analysis or time domain simulation. That is, suppose we inject one particular frequency, this is f sub x, into the input. This change of voltage will change the frequency of the drive. This is the modulator, which changing the frequency of the drive. And this, in fact, will cause a variable output, which will be similar to the input if the signal is small. And I'll talk about it a little bit later. So by doing a time domain analysis on one frequency, we can get the output for that particular frequency. Now looking at the input, this will be the excitation, and then looking at the output, looking at the amplitude of these two, I can get the gain, the ratio between these, and then looking at the phase shift or the time shift between these, I can get the phase information. So this will be for one particular frequency. Now if I repeat this for a range of frequencies, I can actually reconstruct this particular function by having dots here or points here that I'm deriving or getting by simulation, one after the other, and this will reconstruct the curve of magnitude, and of course the same thing, I can get the phase. So this is one way to do the so-called small signal AC analysis, except that it is AC in the sense that it is a small signal superimposed on DC. It's not a phasor analysis. So PSIM simulator has a built-in capability to do exactly this type of simulation. So the AC analysis of PSIM, it does not involve linearization. It is based on the time domain analysis, as I've shown. It is automatic in the sense that you don't have to set the frequencies of excitation one by yourself. It is, of course, for one operating point, one bias point, that is for one carrier that is around a specific frequency that you are running the converter. And it will do the multiple frequency runs by itself. For each one, it will extract the magnitude and phase, and of course, build the curve of the magnitude and phase that you would like to have. Unfortunately, because it is running many simulations, one after the other, that it takes a relatively long time. Typically, for an LLC circuit, it might be something like 10 minutes, which is not too bad. The key elements involved in the PSIM simulation are, first of all, the signal generator or the excitation source. This is an AC source. It is AC, again, a time domain. That's not an AC like in SPICE, which is a phasor source. It is a time domain source. It is sinusoidal time domain. And then we need a probe. That is, we have to tell PSIM which is the output port. So this will be attached to the port, which is the output. Then we have the AC sweep command, and this is its setting. And what we see here is a start frequency, that is where we start the sweeping. We have the end frequency, number of points that we want in this range, flag for points, meaning whether we like the points to be distributed linearly or logarithmically, the source name, that is, which is the source, start amplitude, and end amplitude. Now these are very important, and the reason that we would like to change the amplitude of excitation, that is the amplitude of the source or of this source, is that in a typical converter you'll have a low pass filter at the output. This is to attenuate the ripple, and consequently at high frequency it'll also attenuate the excitation that you are doing here by this analysis. So in order to overcome this and to retain the signal to noise ratio that you want, that is to have a signal which is larger than the ripple, you would like to increase the amplitude of the excitation toward the end. So this is the reason for this second value here. And then there is a frequency for extra point, that is if you have a specific area in which you'd like to have a better resolution, you can specify it and it'll add some points around this point. So what we are going to do then, we're going to inject the signal, we're going to get the output, and PSIM will do for us this job. When we do this, we would like to inject an AC signal, an analog signal, and not here a variable frequency, because there's no way to do this as a matter of fact. You need a modulator. In fact, whenever we are running this type of analysis, we have to include a modulator that will translate the input excitation into a frequency, a variable frequency. We are not interested in this, but we do have the modulator. So in order to run this thing, I have set up a generic modulator here that can be then translated to any IC controller that you might have or you're going to use. The way it is built is very simple. We have a ramp generated by a current source, a capacitor. It is a comparator with a reference here. Once we hit this reference with this voltage, it'll discharge the capacitor, so it'll start again. And we're going to have this triangular waveform. And then we have another comparator at the midpoint kicking and generating a square wave, and if it's at the midpoint, we're going to have a 50% duty cycle square wave. Okay, so this is a generic modulator, and I'm adding here now the excitation. It's also a current source. In this case, I'm showing a voltage-dependent current source. Here I'm going to put the AC excitation, which will change the total current, and therefore the frequency will be changing here. The PC implementation looks like this. We have a current source. This is the current source here. This is the dependent current source. The input to it is a voltage to current relationship. This is the AC excitation. As we have said, we need the AC excitation, time domain excitation for the AC sweep. This is just a probe to look at this point. And then we have the capacitor. This is now the switch to discharge the capacitor whenever it reaches this reference value, which is in this case 10 volts. This is just to prevent, it's like hysteresis, to prevent a lock of this circuit. So whenever it kicks, there's some delay, so let it reset. And again, this is a driver for the switch. And then we look at this voltage. This is a buffer, and compare it to half this value. This is 10 volts, this is 5 volts, and generating the 50% square wave. And in fact, we have here, so we get 2 pulses to 1 and then an inverted pulse. So this is the generic modulator. Now let's have a look just at the constant between, or the relationship between the excitation and the frequency. I'm starting with the VDT equal to I over C, or delta V, and I'm getting here that the 1 over delta V, which is frequency, is this value, or if in terms of frequency to current, it's 1 over C delta V. In our case, delta V is 10 volts, C is 0.1 microfarad, so it comes out to be F over Y to be 1 megahertz per amp, or 1 megahertz per volt, because we have a 1-to-1 relationship between the voltage excitation and the current, or if you wish, 1 hertz per microvolt. Now, as I've said, any IC controller for resonant converter would have a modulator, because this is part of the mechanism that you need in order to control the resonant circuit. I'm showing here the case of Texas Instrument UCC 25600 controller, This controller, the frequency is controlled by current in this port. The current here is affecting the oscillator. Here it is. This is the current coming out, and here we have, this is a current mirror, and here we have the oscillator, which probably will be something like this capacitor, which is charging, as I've done earlier. And they're specifying it at, let's see it here, the 83 hertz per microamp. Sorry, this should be microamp, correct? So if one wishes, we can change the values, of course, of this capacitor or the current and get, of course, the same constant if you want. So here is an example of a LLC converter, resonant converter, half bridge. Here is the modulator. So this is the excitation, voltage, current, time domain current, excitation. This is the DC steady state value, the bias value. This is the discharge and the comparator. And here we have the two signals feeding to the transistor. This is two inductors. This is the capacitor, a bridge rectifier, etc. We have then the output and the AC probe for running. Now this particular design, we have C sub R 0.5 microfarad, L sub R 5 microhenry, LM, which is 6 times, is 30 microhenry. Characteristic impedance is 3.3. Resonant frequency, that is the resonance between the LR, L sub R, and C sub R, is 100 kilohertz. Before going into example of running the simulation, I'd like to point out that we are talking about FM modulation. Now, the time domain expression for the FM modulation is this equation. We have the carrier amplitude, 2 pi, carrier frequency, time, delta F, this is the shift in frequency, FM, the modulating frequency, and then sine 2 pi FM t. So we have here actually 2 or 3 parameters. We have the carrier, here is the carrier. We have the shift in frequency, how much are we shifting the frequency of the carrier. But then we have the rate at which we are shifting this frequency, that is the modulating frequency. Okay, these are 3 parameters here. And the ratio between this shift and the modulating frequency is the modulating index. This is a very important number because it is affecting the sidebands. For small modulating index, like 0.5, we have just about 2 sidebands, the other one are suppressed. And as the modulating index becoming larger and larger, we're going to have more and more sidebands. When the modulating index is small, we call it narrowband FM, and this is in effect very similar to AM. This is like the AM case, we have only 2 sidebands. Now this is the region we would like to work at, because at higher regions we're going to have distortion. Here we're going to have a nice sinusoidal excitation. Here, I mean at the output. Here we're going to have distortion. And this is very important to realize. So we have actually 2 reasons to make the deviation small. The deviation is affected by the signal we are feeding in, the excitation. So we would like to keep it small. Of course, we have to worry about signal to noise ratio so that the ripple will not be too high. But we like to have this excitation small. First of all, because of the sideband. Secondly, this is a nonlinear system, and when the excitation is very large, you might expect some distortion. So let's have a look what is really happening here. Now I'm showing here a run, time domain. This is with the AC sweep disabled. This is not an AC sweep. This is just time domain using the AC excitation as a function of time. That's a running time. So this is the excitation. There are two cases here. One is 1 kilohertz, and one is 10 kilohertz. This is the 10. This is the excitation, and this is the output signal. This is the output superimposed on the DC. We see the DC is about 100 volt, and we are superimposed on it. So we have a case of 1 kilohertz and 10 kilohertz. Now, due to the factor between the excitation and the frequency, we find that here we have a modulation index of 10, because this is like 10 kilohertz, and here it's 1, the ratio between 10 kilohertz deviation and 10 kilohertz modulating frequency. Now, what we see here is two things. First of all, the amplitudes are different, and the reason is, of course, we have attenuation in the output, but what is more important is here we have quite a bit of distortion. And here it looks like a very nice sinusoidal excitation at the output. So this is the way we would like to work. Of course, we have to make sure that the ripple is small. And here we have another case in which the excitation is 0.005, so it comes to be, in the case of 1 kilohertz, 5, and also in this case 5. There are two excitations here, and as we can see, this is quite a bit almost a sinusoidal waveform. M is this was 10, and this is 5, and here, well, it's not that nice as compared to the 1. 1 was very nice, and also here we are starting to see the high frequency ripple of the converter. So it's very important to tune the value of the excitation so as to have a nice sinusoidal waveform at the output with, of course, reasonable signal to noise ratio. And here is just another example. I've run two cases, both of them for the same resistor, but with two excitations. And this is now already the AC sweep. We have, this is frequency, this is the amplitude, and this is the phase. So basically we should have gotten the same curve, because this is two cases are the same cases, except the excitation are different. But because the modulation index here is higher at the beginning, higher than the first case here, we see two different curves which are quite a bit different. And so if you are not careful, you can get something which is non-realistic in terms of small signal transfer function. Small signal, we mean really small signal. That is the slope at a given point. And what happens in the time domain in the two cases, these two cases, and I'm looking now at 2 kilohertz, which is right here, and this is now running the time domain, just looking at the frequency in a time frame. So we see here two modulating index. For the 2 kilohertz, it comes to be M1.5 and 0.5. You see here a fairly nice sinusoidal waveform, and here it's already quite a bit distorted. Now obviously PSIM cannot find the correct amplitude and phase if you are adding these high frequency sidebands, and therefore one has to be very careful to tune the magnitude of the excitation. So here is now a nice run. We have carrier, it's 80 kilohertz. We have two resistances, 3 ohm and 10 ohms. The excitation here is 0.001, and here is also 0.001, but I've added another one, and the reason is just to see if I'm in a good operating point in terms of the excitation. So if we look carefully here, we see here two carriers which are fairly close. This gives me assurance that I'm in a good excitation value, because if the excitation would have caused distortion and harmonics, these two would be different. So this is for the same run. This is for the 10 ohm, while the green one is for the 3 ohms, and this is of course the phase. So what we see here, by the way, is that we have a bandwidth of about, this is 1 kilohertz, this is 2 kilohertz. So the operating point or the bandwidth that we can probably obtain with this LLC is with a simple type 1 compensator being around 1 to 2 kilohertz. Now interesting, if I look here, this is now the static transfer function. Here's the 3 ohm and 10 ohm, this is 3 and 10 ohms. I'm at 80 kilohertz, this is 80 kilohertz here. This, I've generated a curve which is the frequency. This is also frequency, but it's kind of coded into time, and it starts from 0 to something, while here it's actually the frequency itself. So here it is, 80 kilohertz, we are here. Slopes here are the same. We are in this region. This is the nice thing about the LLC converter, that it has a sort of constant gain here for a range of loads. So the slope is about here, but this is again for the very low frequency. So indeed, at low frequency, we see here, these two curves are just about the same. But as you go to a higher frequency, you see the effect of the reactive elements, the inductors and capacitor, etc., and this is why you see this region here. This is now the phase, and this is the amplitude. Let me talk now about some other issue, and that is parasitic elements. Now, if we are going to have here a transformer, it's bound to have some leakage inductance, and this will affect its transfer function. Now, I'm just showing it here by simply adding a inductance here in series. This is sort of representing the leakage of a transformer, which I have not included in order to simplify the circuit. So here we have an extra inductor that represents the leakage. And I've run 3 cases, 0 leakage, 5 microhenry, and 10 microhenry. Well, these are a little bit high because this is 30 microhenry. So this will be like the primary of the transformer. So you'd expect something like 1 to 3 microhenry leakage, but nonetheless, I've done it here just to emphasize what is really happening. So what I see here, that for the 0 microhenry, I see this curve here, and obviously as I'm increasing the leakage, these curves look quite a bit different. For 10 microhenry, it's just something else. And of course, this takes effect also in the phase, and we have here the 3 different phases. So one has to be very careful to include leakages. Now, let me just say that the PSIM AC simulation is very similar, of course, to what one can do on the hardware with a network analyzer, with a frequency response analyzer. And this will be just about the same, and the same problems we have here are going to be there, except that when you do it on the hardware, you can really look at the effect of all the parasitic elements, and here you can just estimate these parasitic elements. So this brings me to the end of this presentation. I hope you found it interesting and that it'll be perhaps useful to you in the future. Thank you very much.